Good morning, my name is Christopher Expósito. I am a PhD student from the University of La Laguna in the south of Spain, and I would like to present you today this work entitled Optimization Model and Heuristic Approach for the blocks retrieval processes in warehouses that has been done in collaboration with my supervisors, Belén, Melián, and Marcos Moreno. Well, the contents of this presentation are shown in this slide. Firstly, a brief introduction about the work, the description of the Q-blocks relocation problem, the optimization model and heuristic approach we propose for solving it, the computational experiments we have carried out in order to check the suitability of our proposals, and finally, some conclusions to be drawn and several lines for further research. Well, as you know, the block stacking is the most widespread strategy used when storing goods in robust load units in such a way that the blocks are placed one on each other. In this context, the order picking can be understood as the retrieval of one or several blocks from their current locations. But unfortunately, the order pickings are known to be the most labor-intensive and time-consuming processes in the context of warehouses. The reason is that every time we have to retrieve a block placed below other ones, we have to carry out relocation movements associated to those blocks placed above it in order to free them up. So in this work, we focus our attention in those contexts in which we have technical machinery that can move several blocks at once. This is the case of vacuum lifters, forklift trucks, key cranes, and so on in the context of maritime container terminal that is our field of research. So the Q-blocks relocation problem can be understood as the problem of retrieving all the blocks from their current locations into a bay composed of several stacks with a maximum number of tiers in such a way that we minimize the number of relocation movements carried out to retrieve all the blocks from their locations. But the blocks have to be retrieved according to the decreasing order of priorities in such a way that we firstly retrieve that block with the highest priority, block number 1. Later we have to retrieve that block with the next highest priority, block number 2, and so on until all the blocks have been already retrieved from the bay. In this context, and according to the relative priorities of the blocks into the bay and their relative positions, we can identify two types of blocks. Firstly, the non-located blocks, that are those blocks that are currently placed above other blocks with higher priority. This is the case of block number 10, that is currently placed above other blocks with a lower priority, higher priority, priority number 1 in the stack 6. On the other hand, we have well-located containers. Those containers or those blocks that are not currently placed above other blocks with higher priority. This is the case of the block number 3 that is placed above other containers with a lower priority, block number 6. So we can carry out two types of operations. Firstly, if we have a technical machinery that can move several blocks at once, Q blocks, we can move at most a subset of at most Q blocks from the top of a stack to the top of another stack. This is the case we can see here in this example, in which if we have a technical machinery that can move 3 blocks at once or more, we can move this subset of blocks to the stack number 5. Okay. On the other hand, we have the retrieval operations in which we can retrieve that block with the highest priority currently placed at the top of some stack into the bay. This is the case of block number 1 in the stack number 4. Okay, we have developed an optimization model to formalize this optimization problem. In this case, it is composed of several families of variables. Firstly, we have variables that indicate if a block is currently placed in a certain slot of the bay. We have variables that indicate if Q blocks are relocated from a given slot to another one during a certain time period. If a block is retrieved from a given slot. If a block has been already retrieved from the bay. On the other hand, we have families of variables that indicate if a block is relocated from or in a given slot of the bay, and to indicate the number of blocks placed above a given block before and after a relocation movement. Well, the objective function of this problem is to maximize the number of periods that the last block, block N, is outside of the bay. With this goal in mind, we have to guarantee that each block has to be in or out of the bay during each time period. In each slot has to be at most one block. On the other hand, that the blocks has to be placed one on each other in such a way that no gaps are allowed into the bay. We can carry out only one operation, a relocation movement or a retrieval movement during each time period. The retrieval operations have to be carried out according to the decreasing order of priorities. We have to retrieve firstly that block with the highest priority, later the next highest priority, and so on until all the blocks have been already retrieved from the bay. This is only a relationship between variables. On the other hand, we have that the number, we have to identify those blocks that are being moving during a certain relocation operation. This is a linearization of the constraints. On the other hand, we have that the location of each relocated block depends on its previous location into the bay and the relocation movement carried out associated to it. Well, in general terms, the location of each block depends on its previous location and the movement carried out. The previous location and the movements we have, we are carrying out. We have to identify the number of blocks placed into on each block to be relocated, and later we have to identify the number of blocks placed on each block after a relocation movement in such a way that before and after a relocation movement, the number of blocks has to be equal in both cases because we have to guarantee the last in strategy used in the stacking strategy. Finally, we have that the relocation of Q blocks from a given slot is allowed only when there are exactly Q blocks being removed. And finally, the relocation movement into the same stack are not allowed. We have here the domain of the variables. For a thorough explanation of this optimization model, and the later heuristic is provided into the paper. But as we are going to see later, the computational times of this optimization model, due to the fact that we are using a large number of variables, is extremely large in several cases. So in order to solve this drawback, we have also proposed a heuristic approach based on the idea that from the description of the Q-blocks relocation problem in such a way that the shorter the number of non-located blocks, those blocks that are currently placed above other blocks with higher priority, the shorter the probability of requiring additional relocation movement in the future. So with this all in mind, the rationale behind our heuristic is to retrieve the blocks as soon as possible while reducing the number of non-located blocks into the bay. So in order to achieve this objective, we try to build stacks in which we only have well-located blocks. So this is the pseudocode of our heuristic. We iterate over each priority of the blocks. At each step, we find that block with the highest priority currently placed into the bay. We identify those blocks placed on that block. And for this set of blocks, we try to determine the largest subset of blocks that have the increasing priority order in such a way that we are trying to move those blocks to other target stacks with the aim of building well-located blocks in the bay. And finally, we can retrieve in that step that block with the highest priority. The idea is illustrated here. We have to retrieve the block with the highest priority, block 1, that is currently placed in the stack number 4. We have 3 blocks currently placed above it, blocks 5, 7, and 13, in such a way that we have a technical machinery in which we can move at most 2 blocks at each step, in such a way that we identify the largest subset of blocks that satisfy the increasing priority order, in this case, the blocks 5 and 7. So we try to determine all the feasible target stacks for this subset of blocks. In this case, we measure the attractiveness of each stack by means of a function in which we consider the maximum priority of a block currently placed in that stack. For this case, in the stack number 1, we have, according to this function, a value of 3, because 3 is the highest priority of a block currently placed into that stack. On the other hand, we have that the stack number 2 is ruled out of the selection process because there are no empty slots to be considered into this stack. For the stack number 3, we have the value of 15 because 15 is the priority of the block with the highest priority currently placed in that stack, and so on. So the idea is trying to move this subset of blocks to that stack in which the future relocation movement is going to be done as later as possible. In this case, if we move this subset of blocks to this stack, to stack number 1, we are going to require additional relocation movement, at least in the time period number 3. Whereas if we move to the stack number 3, we have to carry out at least in the time period number 15. So we have to select it. We have to select one of these stacks as feasible target stack. Well, according to our computational experiment, we have firstly carried out. We have firstly tested the computational performance of the optimization model by means on problem instances with only 3 stacks, 3 tiers, and 2 empty rows placed at the top of the stacks. But as we can see here, we have reduced the number of relocation movements carried out when we increase the number of blocks we can move at once. This is the case. We only consider 1 or 2 blocks because that is the most traditional number of blocks we can move in the context of maritime container terminals. But the computational times are extremely large in several cases. So this optimization model cannot be applied to real-time applications. So on the other hand, we have the computational experiment we have carried out to check the computational performance of our heuristic in comparison with the most competitive approach from the literature, in this case, the heuristic proposed by Kim and Hong. This is a heuristic that tries to solve the blocks relocation problem, in that case in which we can only move 1 block at once. But as we can see here, we have considered larger problem instances. We have obtained similar or better results in all the cases by means of short computational times, less than 1 second. And as we increase the number of blocks we can move, in this case 2 blocks or an infinite number of blocks, we have also reduced the number of relocation movements down to 6 relocation movements on average, while keeping similar computational times, in this case always below 1 second. So we can say that this heuristic can be applied to real-time applications. We are testing this heuristic on a real maritime container terminal, in this case the terminal of Las Palmas, one of the 4th largest terminal in my country, in Spain. And in conclusion, I had to say that this is a problem to be applied in the context of warehouse logistics. We are addressing this problem from the context of maritime container terminals, but from a general point of view can be applied to more contexts. We have proposed an optimization model that can be applied only to non-real-time applications, but we overcome this shortcoming by means of a heuristic algorithm that tries to minimize the number of non-located blocks into the bay at each step. In the future, we are going to try to reduce the number of variables involved in the optimization model in order to improve the computational times required by our optimization model. But we are especially interested on trying to integrate this problem with another one, such as the pre-marshalling problem, in which we have to arrange the blocks before the retrieval, and finally the key crane scheduling problem, in which we have to retrieve the blocks by means of dividing into groups of blocks. An interesting future line of research is tackling the dynamism of the environment, for instance, changes in the priorities, arrival of new blocks, and so on. So that's all, and thank you for your attention.
Okay, questions?
Hi, I wonder how the primal solution if you let the mixed integer program run for as long as your heuristic runs, how the primal solution obtained from the mixed integer program compares to the solution that you get from your heuristic.
In the case of using the heuristic approach.
So looking at the quality of the solution that you obtain from your heuristic, then letting the mixed integer program run for the same amount of time that your heuristic ran, I wonder how the quality of the solution that the MIP would obtain in that time would compare to your heuristic. Do you have some sense of that?
In this case, when we one of the problems we have with the optimization problem is that the time required to obtain the first feasible solution is extremely large in several cases. Probably one of the reasons is that we are not setting one initial feasible solution for trying to obtain the optimal solution, but in the case we are. But other problem is that if we use the heuristic, the solution provided by the heuristic approach in order to provide a solution for the optimization problem, is that the time required for checking the optimality of the solution is even large in some cases. Because the problem with one of the drawbacks with this type of problems is that there are many similar solutions with the same value. And every time you have to move a block from a given stack to another one, or to another one, you have the same increment in the objective function value, but you have to determine which one is the best.
So one thing that struck me about your MIP formalism is that there are a gazillion variables in it. So the first question is, do you think that's hurting the MIP? And the second is, if you didn't use a heuristic approach, but you pose this, say, in, I don't know, PDDL or some planning language, would that reduce the size of the representation and maybe improve your performance?
Well, our idea here was trying to provide a first approach to this type of problems. So, of course, the problem here with the number of variables is that we have always the absolute positions of the blocks during the time period, during all the planning horizon. So our idea is trying to reduce the number of variables, trying to indicate only relative positions between blocks, but that is a future work. On the other hand, the problem with approaches such as the PDDL is that, as far as we know, there are several approaches based on that case. This is the case of one of the authors who presented yesterday, is that all of them require extremely large computational times. So that is the reason why we have to decided to develop a domain-specific heuristic for that. There are no good results so far for this type of problems based on PDDL.
Okay, so thank you. We can move to the next talk. Thank you.